Section 3.2, Calculus of Vector-Valued Functions. We've spent an entire chapter in our Calculus of Vectors class, and we haven't done any calculus. But here's where it starts. We just learned about how to take limits of vector-valued functions, and we found that it's pretty easy. It's the same limits that we used to take, but it's threefold potentially. We have to take the limit of each component function separately. Now that we know how to take limits, we can use the limit definition of a derivative. The limit definition of a derivative looks so much like how it did in Calc 1. The only main difference is that we're dealing with vectors. I am going to use a delta t to represent the difference between 2 points on our vector function instead of an h or an x minus a. So what we're saying is that we have 2 points on our function r of t in the numerator, and they are spaced apart delta t, and then we're dividing by that same distance delta t in the denominator, and to make that go to the derivative, we're letting that delta t limit approach 0. Now, the derivative of a vector-valued function only exists if the function is differentiable. Now, if a function is differentiable, the limit exists. And that's always sounded circular to me, but what it basically means, a limit does not exist, that d in e, if the left and right-sided limits do not match up. So if we're curious, does this limit exist for the derivative function r prime? What we really need to do is check that the left-sided limit and the right-sided limit both produce the same value. And if they do, then we would say that the function's differentiable, the limit exists. Now, most of the time, when we're just trying to find the derivative or determine if a function's differentiable, we can just evaluate the two-sided limit, and if there's no problems, then we know it's differentiable. The only time that we need to go into the details of differentiable is if we arrive at a problem while we're trying to evaluate the limit. So your first shot, try to evaluate the limit. If there's a problem, then we might need to consider whether or not the function's differentiable. We're going to do this in this section only, using the limit to find the derivative function for a vector-valued function. If you remember back to Calc 1, you learned this first and then you learned the shortcuts next. Well, be careful with just blindly applying shortcuts in Calc 3. We're not working with your typical single variable functions anymore. So we are going to slow down, start with the limit definition of a derivative, and I assure you the shortcuts will come later. So let's use this limit definition to find the derivative r prime of t, and the function that we're looking at, r of t, it's a vector function with 3t plus 4 in the I hat direction, t squared minus 4t plus 3 in the j hat direction. So to use this limit definition for the derivative, we need to first find what is r of t plus delta t. Well, we're just going to replace all of the t's in this vector function with t plus delta t. Now that is going to go in the numerator to replace this r evaluated at t plus delta t. But that's going to look really messy. There's a lot going on here. So what I suggest is let's find out what the numerator looks like. Let's do this simple operation, this vector difference, before we plug it into the limit notation. We know that r of t is the function 3t plus 4 I hat plus t squared minus 4t plus 3 j hat. So if we do the vector difference, we're just subtracting the corresponding components. So looking at the I hat components and subtracting here, we notice that we need to distribute the 3 into these parentheses. So we'll have 3t plus 3 delta t plus 4. And then we can do the difference there. See, we have 3t minus 3t, so the 3t's cancel each other out. We do have a 3 delta t with no delta t down here to subtract it from, so that would just come right down. And then the 4's also cancel each other out. So in the I hat component, we're only left with 3 delta t. Looking at the j hat component from each of our two functions, we can see that we have some cleaning up to do, some algebra. I have a binomial squared, so I'm going to use that binomial squared shortcut. And then I need to distribute the 4 into these parentheses. Remember, that is a minus 4, so I'm going to distribute that as minus 4t minus 4 delta t. And then carried the plus 3. And this is the entire j hat component from that first function. And now we can do our subtraction. T squared minus t squared, those cancel each other out. 2t delta t. I don't have another t delta t term down here, so that one would carry down. Then I have a delta t squared. I don't have anything down here to subtract a delta t squared, so that would carry down as well. I have a minus 4t, and I'm subtracting a minus 4t, so those two things cancel out. Minus 4 delta t, there's no delta t term, so that one comes down. And then a 3 minus a 3, those cancel each other out. So the j hat component from the vector difference r at t plus delta t minus r at t. So this makes up our numerator, and we need a plus sign here since the numerator contains both of those terms. So what we are replacing is this yellow box from our numerator with 3 delta t I hat plus 2t delta t plus delta t squared minus 4 delta t. All of that is the j hat component. So the derivative, r prime of t, has that in the numerator. And then in the denominator, we just have the delta t. And of course, we have our limit where delta t is going towards 0. This is where what we learned in the last section will help us out. We are applying a limit to a vector. We're applying a limit to a vector. And so we need to separate the components of the vector. So we're going to have a I hat limit. And we'll have a j hat limit. And just to really highlight that we're taking the limit of the component function and multiplying it by the standard unit vector, I'll pop some parentheses on here. Now if we try to plug in 0 for delta t at this step, we would get indeterminate forms, 0 over 0. Now quick Calc 1 review, 0 over 0 is indeterminate. That means we don't know what it means. It's not equal to 0. It's not equal to 1. At this point, we don't know what it equals. We have to do some algebra to clean up the expression that we're trying to evaluate the limit at and hope that we can eliminate that indeterminate form. In the I hat component, we can divide off a delta t. So actually, we're just taking the limit of the constant 3. We know the limit of a constant is a constant. It's the same constant. So this is 3. And don't forget we're multiplying by an I hat out here. And then in the j hat limit, we have the same problem. If we replace delta t with 0, we get an indeterminate form, 0 on top, 0 on bottom. But what we can do is factor out a delta t from our numerator, and then we divide off the common factor in the numerator and the denominator. So really we're looking at the limit where t goes to 0 of 2t plus delta t minus 4. Our denominator is just 1, so we don't even have to really talk about a denominator. If we replace delta t with 0 in this case, we would get 2t plus 0 minus 4, or 2t minus 4 in the j hat component. Now that we've separated each of our components to evaluate the limits separately, we can see that the limit of our big expression here, where both components were together, it simplifies down to 3i hat plus 2t minus 4 j hat. So we found our prime, the derivative function of our vector valued function, in this case using the limit definition. Now before we move on, let's take a moment here to look at something quite interesting. Our original function r of t, in the I component, we had 3t plus 4. And when we took the derivative, we got 3. Now if we had just taken the derivative of 3t plus 4, we would have gotten that 3. And same thing in the j hat component. We have t squared minus 4t plus 3. The derivative was 2t minus 4. If we had taken the derivative of the j component function, we would have gotten 2t minus 4. And that's the beauty of this class, is that we did this hard problem once, and now we know we can use everything we learned in Calc 1 to find derivatives of vector-valued functions. We just might have to find 2 derivatives for each function. That's not so bad. Just in case that idea happened a little bit too fast for you, let me show you what I mean. We're going to solve this exact same problem. We want to find r prime, but this time we're not going to use the limit definition. Instead, I'm going to take the derivative of each component function inside of my vector valued function. This is going to save a lot of handwriting, a lot of paper. This is definitely the environmentally friendly way to solve this problem. The derivative of the I hat component becomes 3 I hat. The derivative of the j hat component becomes 2t minus 4 j hat. Much faster, much better. Let's do a few more examples using this beautiful shortcut that says the derivative of some vector function r is really just the derivative of each component function of r. So let's say we're working with this first function here, 6t plus 8 I hat, 4t squared plus 2t minus 3 j hat. To find r prime, we just need to take the derivative of each one of those functions. In the I hat component, we get 6. In the j hat component, we get 4 times 2t, or 8t, plus 2. Oh, too easy. Next one. If r prime is 3 cosine t I hat plus 4 sine t j hat, then r prime, 3 times the derivative of cosine. Now the derivative of cosine is negative sine, so that would be negative 3 sine t. Then for the j hat component, it's 4 times the derivative of sine. The derivative of sine is cosine, so we would have 4 cosine t j hat. We have one more down here at the bottom to do, and this one's a little bit trickier because each component function has a product of 2 functions of t, except for that last component in the k hat direction. So we need to do our derivatives. Let's do each one over here for scratch work. We have e to the t times sine t. This is a Calc 1 problem using product rule. We know it's not anything with vectors because we only have the variable t and no vectors inside of this component function. Product rule says take the derivative of the first function, multiply it to the second function, then add to that the first function times the derivative of the second function. The derivative of e to the t is e to the t. Derivative of sine is cosine. We can factor off the e to the t if we'd like to keep things clean. And this would be the derivative of that first component function. So for r prime, we found that the I hat component turns into e to the t sine t plus cosine t. We need to do the similar process for that j hat component. So we have e to the t times cosine t. Using our product rule, we have the derivative of e to the t times cosine plus e to the t times the derivative of cosine. We can clean this up a little bit by factoring off e to the t. So now we have our derivative of that second component, e to the t cosine t minus sine t. And that's the j hat component. We have one last one, and that's the derivative of the k hat component, which is negative e to the 2t. This one requires a chain rule from Calc 1 because we have 2 times t, so that's technically a composition of functions. So I take the derivative of the outside function, which would look like e to the whatever, and that stays the same. But then we need to multiply by the derivative of the inside function, which is 2t. The derivative of 2t is 2. So we get negative 2e to the 2t for the k hat component. So there we go. We're using all of the things that we learned in Calc 1 about taking derivatives of single variable functions. And that's because, again, each one of our component functions is actually a scalar function of a single variable. So this takes a new idea, a vector function, and reduces it down to things that we learned in Calc 1. Now that we know how to differentiate vector-valued functions, we need to talk about some of the rules. In math, we love rules, right? First thing, the derivative of a constant vector. Now, just to clarify, a constant vector, like c, would be filled with constants. There's no variable, there's no parameter here. So this vector, 1, 2, 3, this is a constant vector, whereas the vector r, which has t squared 3. That's not a constant vector because it changes when the parameter t changes. If we take the derivative of a constant vector, the answer of that would be a constant 0 vector. Remember, the 0 vector is not equal to 0. The 0 vector instead is equal to the vector filled with zeros. This is kind of a semantics idea, but it's important to know the difference between 0 and the 0 vector. Our next rule says that any vector function like u multiplied by a constant, not a constant vector, but a constant like c, we can just factor the constant out, just like we did in Calc 1. If we have a sum of 2 vector functions, like the vector function u plus the vector function v, we can take the derivative of each function individually and then add it together, or we could add the functions together and then take the derivative after we do the addition, just like Calc 1. It also works for the difference between two vector functions. It's not only true for addition, it's true for subtraction as well. Next, we have a scalar product. And what I mean by a scalar product is that this f of t is not a vector function, this is a scalar. Anytime I change the input t, that function produces an output which is a single number, not a vector. So I'm multiplying a vector function u by a scalar function f. And we're going to call this rule the scalar product rule. There is a product happening here, but it's specifically a product between a scalar and a vector. F is the scalar, u is the vector. And this product rule follows the same pattern as the product rule from Calc 1. You take the derivative of that first function, that's the f scalar function, multiply it to the second function, u, then add to that the first function, the scalar function, times the derivative of the second function, that's the vector function. And because f prime and f are both scalar functions, we're multiplying in a scalar to a vector. So we don't need a dot product or a cross product there. It's scalar multiplication to a vector. Our next rule involves two vectors. So the last rule we had was a scalar and a vector. This rule, however, is two vectors. And the operation that's happening between them is the dot product. So for this one, let's call it the dot product rule. We are using multiplication. We're taking the derivative of a product, but it's not a scalar product. This is a dot product. It follows the same pattern as the other product rules we've heard of, but notice that we're taking derivatives of a vector and then dotting that with the other vector. And this is an important difference because if you compare this to the scalar product rule, we don't have a dot product going on here, but in this product rule, we do have dot products in each of these terms. Next, we have another vector times vector situation, but this time we are using a cross product. So maybe we'll call this one the cross product rule. Following the same pattern as the other product rules, the only difference is that we are multiplying our vectors, u prime and v, and u with v prime. We're multiplying them using the cross product. Not a dot product, not a scalar product. This situation requires the cross product. This can be a little bit confusing because we haven't seen this before. We haven't seen three different types of product rules until now. But as long as we can pay close attention to detail and look to see, one, are we multiplying a scalar times a vector? Or are we multiplying vector times vector? If it is vector times vector, we need to pay attention to whether or not there is a vector dotted with another vector, or if there's a vector crossed with another vector. And that operation just carries over. So same pattern, but we're producting using different types of products in each of these three scenarios. Another thing to talk about is that in this list of rules that I'm showing you, we are taking derivatives of vectors. So everything that we're starting with, almost everything that we're starting with on the left-hand side is vectors, except for this one right here. Vector dotted with vector is actually a scalar. So what we have inside of these brackets is actually a scalar. We're taking the derivative of a scalar, so the result should be a scalar. However, in every other scenario, we're taking the derivative of a vector. And when we take the derivative of a vector, the result has to be a vector, which is another way to help you remember the derivative of a constant vector is not 0, it's the 0 vector. We have one last rule down here, and it's a type of chain rule. This says we're looking at a vector function u, but inside of u is a function of t. And what this rule tells us is that we can pull out that function of t, take the derivative of it, and multiply it to the derivative of u prime with that function of t still in it. Let's revisit this vector r that I talked about at the beginning. I kind of changed it to where it's t cubed in this last component instead of 3. This vector function has a scalar function f of t inside of it. So I could create a composition here, and if I wanted to take the derivative of this vector function r, what I would need to do is multiply by the derivative of this inner function. And it's kind of a boring example, but we'll see more exciting examples later.